Hello and welcome to the Royal Academy of Engineering's discussion on the future of organ preservation and transplantation, part of our Innovation Incoming series. My name is John Lazar. I'm president of the Royal Academy of Engineering, and I'm delighted to be here at this evening's event as we explore one of the most exciting medical engineering innovations of recent years. And that's where tonight's story begins, with technology that keeps donor livers not just preserved, but actually functioning outside the body, giving doctors more time, patients more hope, and families more chances to see their loved ones recover. This event is a MacRobert Award special, and we're really thrilled to be joined by OrganOx, the winner of the 2025 award. Their pioneering technology is already transforming liver transplantation here in the UK and around the world, and you're going to be hearing much more about that shortly. Before I pass over to our very special host for the evening, some quick points of housekeeping. Those of you who are here with us in person, please remember that we are live streaming on Zoom, and also that the event is being recorded and will be posted online. We aren't expecting any fire drills, and should you hear a fire alarm, that means please follow the instructions of Academy staff to safely exit the building. Please keep your phones on silent for the duration of the event, but you can always feel free to post on X using the hashtag InnovationIncoming. Audience questions are very welcome this evening. We'll get onto those later. Everyone here in the room should use the Slido platform to ask questions, and a QR code will be available throughout the evening. And for those joining online, a link to the Slido account will be available in the Zoom comment box. But I'm going to move away quickly because I want to, without further ado, please welcome our host, Laura Foster, BBC Health and Science correspondent and senior reporter, to the stage. Welcome, Laura.
Thanks, John, for that introduction, and welcome everyone who's in front of me right now here at Prince Philip House in London, and everyone who is watching online. I'm Laura Foster, and I am so delighted to be here today. That's because every single day, people across the world who are living with, say, liver or kidney disease, and their friends and family, because they go through it too, wait anxiously for a life-changing call. A call that lets them know an organ has become available. And for those patients and their loved ones, that call represents hope. It represents a second chance. It presents a future. Now, despite all the many advances in modern medicine over the last few decades and the increasing generosity of donors, about 3 people die every day in the UK waiting for a transplant. And even when someone signs up to donate an organ, there are logistical challenges that come with that. Organs can only survive a short time outside the human body using conventional preservation methods. You know, the ones you've probably seen on TV and in films with like coolers and ice blocks and stuff. And when the time runs out, that opportunity's gone. It's too late. This is a heartbreaking situation, but it's also a challenge that engineers, scientists, and doctors, they've all decided to come together and rethink, well, what is possible in medicine? Enter OrganOx, a company whose pioneering technology is changing the way liver transplantation is carried out around the world. Their system keeps the organ at body temperature. It mimics the conditions it would experience as if it was already in a donor. And this innovation means that donated livers can be preserved for far longer than ever before. And that extra time gives surgeons more flexibility. And it reduces the need for overnight procedures. And most importantly, makes many more transplants possible. The impact is already being felt here in the UK and internationally. Lives are being saved and families are given more time together. And the boundaries of what is possible in transplant medicine are being redrawn once again. And it is to celebrate engineering breakthroughs exactly like this that we present the MacRobert Award. Now, this award is the UK's longest running and most prestigious prize for engineering innovation. It was established over 55 years ago. It has recognised life-changing achievements across every field of engineering, be it AI, aerospace, or from healthcare to hydrogen. And the joint first winners, as was alluded to in that video, were Rolls-Royce for the Pegasus engine, that powered the Harrier jump jet, and Freeman Fox and Partners for the aerodynamic deck of the Severn Bridge. And since then, the award has gone on to recognise more game-changing technologies, such as the CT scanner. You heard before about the roof of the Millennium Dome, but if you're under 20, that's the O2 in London. And the Raspberry Pi microcomputer. Today, the MacRobert Award is proudly presented and run by the Royal Academy of Engineering, with the generous support of the Worshipful Company of Engineers and the MacRobert Trust. So what you got to do to win, eh? Well, you need an engineering innovation that is not only truly groundbreaking, but it must have tangible societal benefits, and it's got to work commercially as well. The winning team receives a shiny gold medal, a £50,000 prize, and a weekend away at Doonside House in the heart of the MacRobert family estate in Aberdeenshire. Supporting and celebrating enterprise, innovation and skills across the UK is a vital part of the Royal Academy of Engineering's work to engineer better lives. And the MacRobert Award seeks out and champions the best of British engineering and technology innovation, which is changing the world for the better. Now, I've spoken probably for far too long, so let me show you what makes this year's MacRobert Award winner so special.
Our innovation is directly saving patients' lives. What we created in OrganOx is a platform technology which currently can serve the liver and the kidney transplant space.
The OrganOx team has developed the world's first fully automated machine capable of keeping an organ alive and functioning outside the body.
Normothermic machine perfusion is quite complicated as a system.
As organs return from a semi-cold dying state to normal body temperature, they experience huge changes in oxygen consumption, glucose consumption, resistance to flow. We had to develop fully automated control algorithms that enabled organs to be kept alive in a completely automated manner.
One of the biggest challenges is to make sure you design a device that is not only engineeringly brilliant, but also can be usable by various clinicians and surgeons across the globe.
This hasn't been done before because biology really teaches engineers a lesson in humility. This technology can enable safe transplantation of over 70% of organs that are currently being discarded. There are on the order of 5,000 patients who wouldn't have been alive today without this innovation.
OrganOx has done something truly incredible. What blows me away is how elegantly engineered their solution is. Fully portable, fully automated. Behind that simplicity is some serious science. Artificial intelligence, fluid dynamics, gas analysis, all designed to keep the organ healthy for longer. It's medical brilliance powered by engineering magic.
Please join me in welcoming to the stage right now the Chief Technical Officer of OrganOx, Professor Constantin Coussios.
Thank you, Laura. How do I describe in the simplest possible terms what the OrganOx technology is? I love this analogy from Wired magazine circa 2011. This machine is so good, your liver will never know you're gone. As I've loved this line for many years, I came to realize over the past decade that it does an amazing job at describing what the technology does, but it completely fails to describe the most important thing of all, what the technology means. And what the technology means, we have heard a little bit about today, in simple terms, is the gift of life and the gift of time, not just for patients, but also for surgeons and clinical practitioners. Let me explain. The technology has been in use now on 4 continents in 12 countries, including the United States. And I got to meet a few weeks ago Vijay, a lead transplant surgeon at one of the largest, if not the largest, transplant center in the United States. We had corresponded and exchanged a few WhatsApp messages, but I'd never met the man before. And he arrived in Oxford holding a 2-year-old child. And this person I'd never met moves up to me, gives me a hug, and hands me their child to hold. And I said, "It's lovely to meet you." And she goes, No, it's lovely to meet you, because if it weren't for your technology, I would never have seen this child grow up. I have actually been at home from 7 p.m. every single day for the past 2.5 years, I've caught up on sleep. I hardly ever operate on weekends, something I didn't think I was entitled to as a transplant surgeon through all my years of training. And as a result, the majority of our current fellowship applicants to transplantation programs at Tampa are women, and that has not happened in over 4 decades. The second story I will forever remember is Connie, one of the first patients who got transplanted with an organ retrieved by the University of Birmingham that would have, in the old world, been binned as unusable. It was placed on the OrganOx machine, it was found to be viable, and Connie was transplanted. And I got to meet her for the first time many years after the clinical trial was over, circa 2021 in Paris. And she didn't hug me, she did something rather different the first time I met her. She walked up and hugged the machine, and then hugged me. And she said in her subsequent speech that if she hadn't had that opportunity, she was older and she didn't want to take an organ away from someone else, she wouldn't have actually been around to see her children graduate from university or PhD, her first grandchild, and the last 30 years would not have come into being. Now, the MacRobert Award was, for me, the pinnacle of my career today. I'm already starting to sense it's about to be eclipsed tonight. And I'm immensely grateful to the Academy, to the MacRobert judges, to the whole engineering and MacRobert team at the Academy for this extreme and extraordinary honor. And a lot has happened since, including this completely unexpected and huge acquisition of OrganOx for one of the largest and unfathomable sums ever seen by a medtech spin-out in the UK. But none of this would have happened if it weren't for people, and none of this would have happened if it weren't for a common mission and message between my co-founder, Peter FREng, a transplant surgeon, and the entire team that I got to journey with, that we actually never cared about that aspect of things. The only thing that brought us together and that kept us not sleeping on operating room floors, as I mentioned earlier, working through the night, was a desire to bring this extraordinarily complex technology no one believed in into hospitals to achieve unprecedented societal impact for patients and for people working in the clinic. That is our magic superpower as engineers, as technologists, as entrepreneurs, is to actually build technologies that change lives. And for Peter and for me, value, that sort of unfathomable value, could only ever have been achieved as a consequence, not of hype, but as a consequence of real impact achieved in lives. I'm here tonight to candidly and without filtering share with you my battle scars and everything that the last 28 years have taught me, in the hope that we can together use the extraordinary multidisciplinary UK innovation ecosystem to see many more and far greater successes emerge over the next few years. Thank you for having me. It's a huge honor to be here with you.
Thanks for that, Constantin. I can see it's still kind of sinking in, the win, right?
Any day enough.
Do you find yourself thinking a lot about how far you've come? Tell us what it was like when you first had this idea.
When we did the first experiment with Peter, which was in circa 1996, 1997, the technology was the size of 2 upright pianos. It had about 1,600 control variables that could only be tweaked by 3 people in the world. And it was completely unusable by anyone other than Peter, myself, and the other 2 research fellows who were involved in the project. And we spent a decade trying to convince, first of all, ourselves this was something that had legs, and followed the evidence. One of my favorite quotes is, "In God we trust, all others bring data." Never engage into a 28-year project without some solid, pretty robust evidence that what you're about to do could have a huge impact. And the early days were really tough because raising capital and getting people to believe that such a risky technology could ever be brought to the patient's bedside was near impossible. So when we started, you needed a camel and a compass in a conference to find the room where the talks were being held about organ preservation and machine technology. And today you can't walk into a transplant conference without it being dominated by these technologies. But it's been an incredible journey, and we'll have the chance to talk a lot more about it. It's completely transformed itself from a company of barely 3 people for 3 years to almost 300 people today at the time of the acquisition by Terumo.
And you mentioned just then that you yourself would struggle with the confidence in the project at times. How do you keep a team buoyed and energized in what you're doing?
Starting with co-founding a company with someone, where I got really lucky, and what I firmly believe is one should never start a company with someone they wouldn't consider donating a kidney to.
Right.
So it was extraordinarily.
Is that just because of what you were doing,
Nope,
or just
the
for everyone?
criterion applies even beyond transplantation. So Peter and I had this incredible connection pretty much from day one. He was originally my master's supervisor, then evolved into a colleague, a friend, a mentor, a co-founder. But we shared a common set of values, and to show how strong that is, I have 3 sons, and the youngest is called Peter, and that's not a family name. The second thing is, once you create that culture and that ethos, being very, very clear about what it is you're about, I think is very, very important. Because today there's kind of this very strong perception that people join companies for salaries, for benefits, for career progression. I actually fundamentally believe people choose their working lives driven by passion. And if they can find something that fundamentally lights up a fire inside them, then they will journey with you. And one of the great achievements I think we did was to grow a skeleton team from 2, 3, 4 people to today a team of over 70 engineers in 3 countries, always with the same set of values and never actually losing people along the way. So the team that received the MacRobert Award started mostly with us between 2010 and 2015, and we're still around by the time of the MacRobert Award almost 15 years later. And we worked for years together without really counting hours or overtime or weekends. This is a very grueling procedure because it's a 24/7 sort of approach. And I think that sharing of values, that sharing of passion is the fundamental driver in uniting people from different disciplines.
That keeps the spirit going, the shared passion. The video we just played mentioned that 5,000 lives have been saved by this technology. That's got to be higher now. How many lives are we talking now?
So people very often focus on the hockey stick in value, but I think my favorite part is the hockey stick in impact that these companies achieve. So last year we were performing about 4 transplants a day. As of this morning, we were performing closer to 12 transplants a day. So the usage, the utilization of the device, of the technology has tripled in the span of a year. And so the rate at which we're saving lives has increased significantly. So it took us the better part of 2 years to go from 4,000 to 5,000. Since the MacRobert Award was filmed, we're now at almost 7,500 lives saved and accelerating.
And do you get notified every time it's been used? And
we have a counter. This is actually what drives us as a company. You know, every donated organ counts, and there's a counter constantly on display in different locations.
how big is it? What's the sense of place?
So we have it in different formats. So some formats are digital, some formats, some people have it as a little tab on the desktop. It's kind of something that we intentionally provide and promote across the company to remind people why it is we're doing what we're doing.
That's great. Another favourite part of that video was when you said, of mine anyway, was when you said biology teaches engineers a lesson in humility. Tell us some humbling moments you've had in this process.
So when I started working on this, I was educated very rapidly by some surgeons and a perfusionist. And I remember sitting there thinking, it's wonderful that they're doing this by twiddling knobs, but I'm a brilliant engineer. I can model this away in about 6 months, built a predictive controller that is going to anticipate every little thing that the liver is going to do. And therefore building a control system is going to be child's play. 28 years on, I'm still trying. And the reality is that biology is one of the most nonlinear systems known to people. So I had the pleasure during my undergraduate education in a place which has an Oxford professor shall not be named, to work with the developers of the Harrier aircraft. That was one of the most complex nonlinear systems known at the time, because you have to stabilize these vertical takeoff aircraft. The nonlinear dynamics I learned on that did not work for a human liver. So there is a whole other complexity of 1,600 variables interacting with each other in unpredictable ways. Simple example, if you give a liver if a liver is starved, it's actually going to change its arterial resistance to flow because it wants to let more blood in to get more nutrition. But in doing that, it's going to completely alter its oxygen consumption because it wants, so everything is interconnected in ways that we cannot yet hope to begin to understand as rational Cartesian engineers.
You're answering this in a very calm way, but there must have been moments where you were like, why isn't this working?
There were, but what's really interesting is in this type of really adventurous development, it's never the things you spend much time worrying about that gets you. So my biggest concern was my algorithms were going to let us down someday, and we're eventually going to come across a liver or a kidney where they wouldn't work. That hasn't happened, but the two things that really threw me was how to package a disposable set and how to build a trolley. Right. And so I love this old adage about the sort of known unknowns and the unknown unknowns. It's the unknown unknowns that will floor you every single day of the week, and you never know what they are. So they just come your way, and yes, you panic, and then you deal with it.
It's an impressive bit of kit. I think usually when there's an impressive bit of kit, there's usually quite a high price tag. How easy is it for countries around the world to be able to afford to use your machine?
So as mentioned from the very first day this technology was conceptualized, adoption was the key driver above all else. And so we decided very early on that no one in the world was going to have to pay for the machine itself. We actually pre-build the machines. This is a major barrier to a lot of healthcare systems around the world, is what's called CapEx. And so we leased the devices free of charge in return for a commitment to use a certain number of times a year. And the pricing is not the same across different territories, because one of the things that is less known and less understood is the cost of actually supporting healthcare in different nations varies widely. Are there any Americans in the room?
No, one on their own.
Please forgive me for what I'm about to say, and if she does react, please constrain her. So we spent 10 years working with UK transplant surgeons. You gave them a machine, you trained them for 2 procedures, and you never heard from them again until they were ready to place their next order. In 5 years in the United States, every single procedure has had to be supported. We've had to put people around because there is a completely different aversion to risk. So the cost of actually supporting and deploying these technologies is very culturally driven. And so to answer your question about cost and pricing, the studies that have been done, we have always managed to price these technologies so they cost less than 10% in any one territory from the overall cost of transplantation. Now, an important consequence of this technology is liver transplant centers that have been using this report a 30 to 50% increase in the number of organs being transplanted. But even with that increase, even by paying for the technology, their overall cost is actually lower. And that is because the people who get a transplant then don't have to be supported on intensive care units whilst awaiting a transplant. So there's a massive cost saving in terms of downstream costs that the technology is enabling.
So there's no barrier to any country being able to use this technology?
There is no barrier, although one of the great things that we hope will emerge from this latest development of the acquisition of OrganOx by Terumo, a Japanese multinational biomedical company, is that we will be able to do vertical integration. I go to a component level of how to make everything about this device significantly cheaper and more commoditized. And it's a very difficult thing to do when you are an industry that does 7,000 procedures in total. Most of these technologies scale in the hundreds of thousands per year. So when you partner up with someone who has that scale, you then get an opportunity to go to the next level of simplification and cost reduction. And therefore, we hope that one of the big things that will come is massively increased patient access and international access for patients around the world to this technology.
What sort of targets have you set yourself when it comes to that?
It would first of all be very nice to be able to make the technology smaller. So it's not just about cost, it's about making it really simple to transport, really simple to use. And so these reductions in vertical integration will make it considerably lighter, considerably easier to use. But what I would like to see is that, there's today about 30,000 transplants happening in what we call the sort of the Western or the wealthier countries. But there's an opportunity of about 50 to 60,000 transplants globally. What we saw in the Western world is we're rapidly taking 30 to 40 to 45, so 50% increase. My target is, can we take those 50 to 60 and make them 80 to 100 in the next decade?
So I was about to ask, what's next for you then? Apart from that, are you looking at other organs?
We had the privilege of testing, and I know we have a very distinguished kidney transplant surgeon with us tonight, the technology for kidney. And even though it sounds very similar, it's actually very different. It's about a 10th or a 5th of the weight of a liver. Unlike the liver, it has one inlet and one outlet, and it also has, when working, the very nasty tendency of peeing your entire circuit volume out in an hour. So doing it for a kidney is actually remarkably challenging. We just transplanted the first 36 patients in Oxford in the UK. So that is the first sort of next frontier, is to broaden access to the technology to other organs that are currently very poorly served by these technologies. But the next barrier beyond that is to move beyond transplantation to 2 or 3 completely new spaces.
Ooh, what are those?
So the first one of these is that there's a very large population of patients who have liver disease, who suffer from what's called acute on chronic liver failure. That is a temporary and potentially reversible state for which currently there is no treatment. So we have partnered up with a Boston-led technology that has produced pig organs that have been genetically modified to be compatible with human blood. And what we do is we use our technology and those organs to connect the machine to a patient and effectively use it to perform liver dialysis whilst the liver is underserved, making it possible for them to spontaneously recover and no longer need a transplant. And that technology has just been granted permission to enter clinical trials by the FDA. So this is not an imagination anymore. It's going to be reality in patients in the next quarter or so. And then the final 2 things that this technology can be used for, we can actually use them to extensively test drugs. So the development of pharmacological treatments has a very, very long and very risky progression to human trials. And at the moment, part of the reason why drugs cost so much is because they cost so much to develop. Yeah. Well, if we can keep every single organ or almost every single organ alive and functioning outside the body, we can actually test the drugs in human organs without a human attached. And so I think the next frontier is to actually achieve integration of this model with pharma companies and with regulatory bodies in order to accelerate and reduce the cost of new medicines when they reach the NHS.
Before we bring the rest of the panel, I've got to ask you, because you mentioned it in your speech, about OrganOx being bought over this summer. Some people might say, oh no, this is a shame. UK business being bought over by a big global company. What do you say to those people who are worried about the future of UK medtech?
It's a very good point and a very fair point. I think, first of all, we have to celebrate our successes and say, even before this acquisition, a British-born, British-developed, grant-funded idea was able to start saving the lives of patients in 4 continents and 12 countries. Let's not lose sight of that. But there comes a point in any technology where you've got to be able to scale it up to an extraordinary level in order to help it realize its impact. And that opportunity doesn't always obey national boundaries. So if your mission in life is to develop technologies that have an impact on patients, you do what's best for those patients. And what was best for those patients in this particular case was this particular move. The other aspect, which I'm very pleased to say, is that the company being bought out doesn't mean that the UK loses out. So when a company is bought, not sold, one has the opportunity to make certain things happen. And one of the things that has happened here is the R&D, the majority of the R&D will remain in the UK for the foreseeable future, will actually benefit from much greater investment. Mm-hmm. And by having these successes, we can now laud to the rest of the world, and having the R&D capacity, we can keep generating these successes until someday we can become our own version of Silicon Valley and have the capital and the local ecosystem so that these technologies never need to leave.
Just before we bring on the panel, where would you put the Silicon Valley of the UK?
Somewhere on the British Isles.
Clever. Right, thank you so much, Constantin. Before I bring the additional panelists on, I'd like to point out that in about 10-15 minutes time, we will be taking questions from the audience. So there should be a QR code flashing up on this screen very shortly, and it should be appearing online as well. Scan the code, submit your questions, and I'll put them to the panel. So please join me in inviting to the stage Dr. Alison Vincent, the chair of the MacRobert Award judges, and Pankaj Chandak, who, oh my goodness, such a long title, let's go for it, is a paediatric transplant fellow at Great Ormond Street and Evelina London Children's Hospitals and a postdoctoral research fellow at KCL and UCL Institute of Child Health. Please welcome to the stage. Right. So there's a question for all three of you, but I'll start with you, Alison. OrganOx is this kind of classic example of collaboration between engineers, clinicians, scientists. How important is that kind of work?
It is incredibly important because you're trying to solve a very complex problem, which is not going to be solved by one vertical. So in this particular situation, you've got clinicians who understand the issues that the surgeon is under, but then it needed the software engineers to create the displays on front of the units, to do the clever data transition from the active device to a cloud system, combined with, quite frankly, brilliant physical engineers who created a box to transport the equipment in. So not one discipline could solve that set of problems. They actually needed to collaborate to come up with a solution that they did come up with.
How much more of that do we need to be doing here in the UK?
I think some of the universities are moving more to interdisciplinary research. And I think that's definitely what we need to do. When I look through all of the 3 finalists that we had within the process, all 3 of them were cross-disciplinary companies. So people who actually understood the benefit of combining different sciences like fluid dynamics and glass technology, the whole scope of different examples of engineering coming together to solve a business problem.
Pankaj, you were nodding as Alison was speaking. What do you think about engineering and clinicians working together?
Yes, well, firstly, thank you for inviting me and congratulations again, Professor Constantin, and to Peter FREng and the entire team. It's fantastic. I think it's very exciting, actually, as a clinician and someone who does clinical science, working at that interface between biology and medicine and engineering, because we as clinicians are patient-facing. We see the patients with the problems and we want to come up with some sort of solutions which may not be in the realms of surgery or biology, but we have to rely on other disciplines. And I think at that interface is where the real creativity happens, actually. So I think it's important. It's important for our own growth intellectually as well. But also the excitement of working with a multidisciplinary team is where I think the science will progress towards better patient outcomes, as exemplified by OrganOx. So.
And Pankaj, you've probably spent the most time in being around transplant surgery out of all of us. You in fact did one this afternoon and then came straight here, which is just fantastic. How much of a difference is the kind of kit that OrganOx is developing? How much of a difference is that making?
So thank you, Laura. So it's a good question. So we use machine perfusion at our hospital. We use it clinically and experimentally. So if I've got an organ that I'm not quite sure whether it's usable for a particular recipient, we call it a marginal organ. Usually these organs from older people that may have disease within them, such as diabetes or hypertension. We're not quite sure whether that's going to be appropriate for that particular recipient. Instead of subjectively looking at it and making a decision, we can get objective physiological data in real time from a normothermic machine perfusion system that will give me a readout of how that organ is behaving metabolically. For a kidney, for example, with respect to how it looks, whether it's making urine, we spoke about urinary circulation earlier, and what the blood flow of that organ's like. And then if it reaches a certain criteria, we can then appropriately consent the patient for that procedure to say, look, we've assessed this kidney. It appears to be marginal initially, but on the machine, it seems to reach a certain criteria where we feel it would be potentially usable for you.
How often are you surprised by, say, you or your team look at a kidney and go, don't think so, and then the machine says, actually?
Yeah, I mean, in our own centre, we've done almost 20 to 30 kidneys similar to on the machine, and we're part of a national program looking at quality assessment of kidneys using machine perfusion. We discard about 11 to 12% of human kidneys every year, organs, because of, they're not usable for whatever reason. So I think this technology will certainly help increase that pool, or certainly tap into that pool. It's an important source of organs, I think. So yeah, it's something that's been validated and used clinically.
And what difference has that made, in the mood of clinicians such as yourself when it comes to the...
Well, I think now with OrganOx, we can probably sleep more.
Everyone's mood will be improved already just by now.
So certainly using machine perfusion systems like this can help plan logistics for us. the NHS is obviously a limited resource of funding with staff and access to theatres, where we're competing with other specialities in trauma, for example, who need access to theatres. So machines and innovations like OrganOx can actually help us plan logistics and secure staffing, and to do things in more controlled environment than a slightly uncontrolled environment.
But how does that make you feel emotionally, mentally?
I think it's fantastic. I mean, for me, the real excitement is the experimental side, actually, of this machine, taking it to the next stage. Speaking about drugs and, you know, how we can actually modify, manipulate these organs using the machine before connecting it to the human being by affecting the endothelium, putting drugs in, protecting it against rejection, crossing difficult immunological barriers, think about organ regeneration and repair, and even CRISPR gene editing therapy to delete particular genes that may be deleterious to the patient. I think that's going to be really exciting. So it makes me feel pretty good. Yeah.
How does it make you feel hearing that?
Amazing. You know, it's you never get tired of hearing it. I mean, one of the great things in Austria, which was one of the most rapid adopters of this technology, they no longer do nighttime or weekend transplants anymore. So it's, you know, and I remember actually a very early story at King's in the very early days of testing this technology, where we arrived back with the machine and a liver on board, and there was one operating theatre and 3 organs that arrived at the exact same time. And the theatre staff were pulling their hair, trying to prioritize, and I was able to say, don't worry, this one can wait till tomorrow. And it was an extraordinary sort of paradigm shift for people going, oh, I can actually plan. I can actually plan is something that was previously unplannable. So hearing this transformation from practitioners is absolutely incredible.
And just to add to that, that's actually a very stressful situation for us. Often we do get multiple organs arriving at the same time for different recipients, and each operation could take several hours. And then while the next organ is still in the icebox, and so the cold ischemic time is ticking on now, and then the third transplant you have to do, that's now, you know, much further down the road. So it affects the quality of the graft, and that creates a lot of stress on the staff to get things in quickly. You may not have access to theatres. So that's a very stressful situation, actually, what Constantin was describing for us.
Constantin, before we came on stage, you were telling me about how you used to sleep on the floor while transplant surgeries were going on in the early days of the machine. Do you still ever get so nervous that you have to sleep next to the machine?
I think that never leaves you. And you know, one of the big learnings here was, as a technologist, as an inventor, you know, live and breathe your invention, follow it everywhere it goes, understand how it interacts with its natural environment. And I have a couple of stories to share and from my dark past. So before sleeping in operating theatres, I used to sleep with pigs a lot, which is not something I talk about because a lot of
you've got to explain why.
a lot of the preclinical research was done in large animal models, so we had to look after the donor and then the recipient. And on a skeleton crew, you do what you need to. But I will never forget one of the first transplants we did actually at King's, and we had retrieved it from somewhere outside the ring road, it doesn't matter where. And it was transplant, it was liver number 2, and the machine started beeping like there was no tomorrow. There was an occluded line. And I had to stop by the side of the A4, actually take the machine out of the ambulance, and in the middle of the road, keep sterile conditions, open the organ, unpinch the tube that had become occluded, put it back on and put it back inside. What I'll never forget is the people driving by who were doing this, and I've never been able to drive that particular part of the A4, feeling the same ever since.
Get a little plaque put up. As the nominations open soon for next year's award.
They do.
What advice would you give to people who think they have an idea or a product that they think could do really well?
Yes. So answer the exam question is the advice. I'm absolutely thrilled about the MacRobert Award because it's very special, because it has this trifold set of criteria for being successful. It has to be genuine innovation, and obviously we're hearing that in spades tonight. It has to be something really unique. It doesn't have to be in medtech, it can be any aspect of engineering, but it has to have real societal benefit. We're not just solving a problem for the sake of it. We want to change the world. But also we find a lot of things come through in that vein, but not many of them are proven commercially. So that is also the third aspect which you have to answer that question. There's guidance on the website. We've updated it to help people work out how to answer those questions. But I encourage you, look at all those three areas, represent your invention in those three lenses, and best of luck for next year.
Cool. Thanks, Alison. Right, so let's move on to the audience Q&A now. I've had a bunch come through here, but if there's still time, if you want to submit a question, pop it, just use that QR code and it will come right to me. So first question's from Sheridan. They haven't said who it's to, but I'm thinking it's for you, Constantin. How do you balance the excitement of cutting-edge innovation with the need for robust clinical validation and patient safety?
That's a very good question, and I think this is where Peter and I have had a very good sort of counterpoint and complementarity, because I'm very, let's do it yesterday, and he's very, slow down, we need to make sure that this is the right thing to do. And I think you need both types of people in an innovation ecosystem to make things happen. I think being well-trained scientists and working in clinical medicine is a very important training in managing to design trials that properly assess evidence. One of the things we've always done all along our journey as OrganOx, and is very unusual, is we have published every single thing we have come up with. So every year you'll find between 3 and 5 publications describing to the world, putting it to peer review, wanting to hear from other people around the world what we're doing wrong, what we should be doing better. And that has helped us get continuously better. So you do the innovation, then you put it out and you hear the feedback. Then you move to the next step. And when the time comes to test it in humans, you take a very, very cold-hearted view as to, do I believe this is safe? Would I actually put my own child, my own mother, through this procedure? Have I done everything I can to de-risk it? I have never forgotten the first time we connected that first liver that was going to be transplanted. And I can tell all the engineers in the room, the one thought that went through my head is, I hope I didn't miss any important lectures, because if I did, someone is about to die. You have this huge sense of responsibility that it rests with you to have made absolutely certain that what you're about to do is safe and effective.
Pankaj, you're nodding along through that.
Yeah, I mean, ultimately, who's at the end of this chain? It's the patient, actually. So, so anything, any innovation that you do, or any science that you do for patient benefit, has to have patient safety as number one, and that's the ultimate goal. I mean, Joseph Lister famously said, who's a pioneer of antiseptic surgery, he always used to say, there's only one rule: put yourself in the patient's place. And I think that's a very powerful aphorism for any healthcare professional, but also any engineer or scientist working on medtech, I think. So always put yourself in the patient's place. What would they want? And they would want you to be treated as their own family member, really. It's as simple as that.
And I'll add one thing to this, which was definitely a culture shift. We spend relatively little time as technologists really learning how to understand the end user. And one of the big paradigm shifts from starting OrganOx to getting further along was, when you build a clever technology, you go, well, I can train people and it's their responsibility to use it properly. By the time you've done this for a few years, you realize if they get something wrong, it's your fault. It doesn't matter. One of the great conversations I had with the CEO of another company that does something similar called Transmedics in Boston. One of the few things we've ever agreed on is whether it's the doctor's fault or the machine's fault. It's the machine's fault. If in the procedure you have not actually anticipated all the possible ways in which a well-intended or less well-intended user might break it or cause a safety concern, it's on you. And that's actually a great principle to bring with you into designing technologies for patients.
Oh, yes.
And also that's where the collaboration thing comes, because you'll have people who look at things in a different way, in different risk perspectives, they'll be able to join that conversation.
It's a bit like robotic surgery, just to add to that very quickly. When people are now thinking about autonomous robots operating on patients, but at the end of the day, if that autonomous robot somehow has a system malfunction, you still need a surgeon at the end of it to take over. And I think most patients would want that.
This is a question, they've not given their name, but it's for all of you. What advice would you give to engineers or researchers looking to make their mark in healthcare innovation? Pankaj, we'll go with you.
Okay, I mean, for me, I think it's to address address the question, the important biological question here. What's the important health problem that you're addressing? I think that has to be the biggest thing. And is it going to make a difference? So I think that's where the clinicians come in on the shop floor effectively, because we're patient facing. We can try and help identify some of those issues and what those problems might be. So I think that's probably the biggest motivation, is what's the question, and can it be done? Is it feasible? And will it have a real palpable outcome?
Constantin, what was your add?
I was asked to condense my thoughts for a recent lecture, and I was trying to remember what I put on that last slide. This is why I was looking pensive, but I will capture the following. Don't be a solution in search of a problem. Actually solve a problem. And I think this expression I love, in God we trust, will others bring data. For me, in healthcare innovation, it translates into you must have a proven link between what you're doing and how it benefits patient care. There's got to be a direct causal proven link between what you're doing and what benefit it will bring. That's one. There's a couple more, which is it's very, very important to be solution driven, not technology driven. So understanding what the user needs, not being enamored with one's own technology. It's got to be the solution. But actually, the more you spend trying to understand a problem, the more you realize something different might be needed, a companion technology. It doesn't matter. What matters is solving the problem. And then maybe the final thing is, particularly in health technology, we tend to sort of devise things and then see how they might interact with users, then see how we might get them approved. That's completely backwards. So one of the things I discovered in health tech and med tech is it's an onion. And to use an engineering term, the outer boundary condition, the outer layer of the onion in all of this is regulatory. The next layer is usability, and then comes the technology. So spend a lot of time at the beginning understanding the regulatory context and the users.
Do you want to add anything?
I was going to say that the person I forgot in that original collaboration thing was someone who really understands. You're really talking about product management, so someone who understands the markets you're trying to get into and the barriers that you'll face from regulation or from how society works in that region.
Yeah, so important to have all those elements when you're building your team. Amir has got in touch and said, within recent years, AI tends to be the topic of conversation within the development of any technology. How do you see AI impacting the innovation of organ technology? That was a grimace from you, Constantin.
No. It's so I'd love to hear from my other panelists who probably know as much, if not more, about AI than I do. But one of the things that I think people misread about AI is it can tell you great things, but it can't tell you things that are in the original data set you're analyzing. So unless you've measured something, unless you've captured a particular parameter, AI is going to find it very, very difficult to tell you something that isn't described as a dimension in the original data set. Now, I think what it can immediately do in organ preservation is, one of the really big challenges in developing the OrganOx technology was finding one set of control algorithms that would work for every organ, irrespective of whether the organ was big, small, old, new, had been out of the body for many hours, etc. That was already difficult enough, but then you have another layer, which is different surgeons retrieve the organs. People operate or behave in different ways. They put in cannulae and interact with the organ in different ways. So the opportunity to actually use AI to make things adaptive so that they can wrap around a particular user, a particular organ, a particular practitioner is, I think, one of the biggest opportunities we have in organ technologies where AI will be transformative. The second is we have stayed shy of telling a transplant surgeon, you should transplant this organ, you shouldn't transplant this organ. But as we build thousands and thousands and thousands of cases, we're now starting to have the data to say, well, if your organ is behaving like this, it probably has a 95% probability of being okay, and it's behaving like that. It's probably got a 1% probability of being okay. I'm not making the decision for you, but I'm at least presenting you with that information on your fingertips so that as the clinician, you can make a more informed decision.
Pankaj, would you like to come in on that?
Yeah, I mean, just going on from what Constantin was saying, I think for us, the biggest thing about AI and organ preservation, I think, and organ function is can we use AI to predict how an organ will behave, but also what it will be like in 5 years' time, 10 years' time, because that's actually our end point, actually. We want this organ to have maximum longevity. So can we use all the integrated data derived from the machine, all the physiological parameters, perhaps combine that with the biopsies that we might take on the machine, combine it with the demographics of the patient, put all that into an algorithm to say, hey, this organ may last maybe 10 to 15 years, and this is its trajectory. And I think that's probably where the next vision would be for AI in organ preservation, I think, as well.
How long do you think it will be until we have that data that could be fed into an AI machine?
At the exponential rate at which it's growing, we're talking 2 years.
Yeah. 2 years.
And I was having an amazing conversation with Alison right before tonight, where we're talking about digital twins. And it's interesting that this word is used across many areas of science. So I think what we're all talking about is actually having a digital twin of the patient and the organ, so that we can see that when we couple them together, what might actually happen in their future in a reliable way without actually having to do it.
I mean, with all these models, it's all about the questions that you ask. And again, you'll still need the clinician to train the models to understand the questions that you need to ask to work out the longevity of this organ or not.
And you still need the engineers to help the clinician as well. Boy, we've touched on this earlier, Constantin, but a couple of questions have come through about the cost of the product and sort of focusing on countries in Africa, which the machine isn't in Africa yet, is it? How close are you to a low-cost version of a product, which could be incredibly useful in places like Africa?
I think the cost is one parameter, and as I mentioned earlier, I think as how common this procedure grows and vertical integration increases, cost will increasingly become less and less of an issue. But we must not forget we're dealing with the most precious gift of them all here, and this is organ donation. And perhaps the far bigger challenges in some of these other parts of the world, which I am very keen to serve, is making absolutely certain that the proper systems, checks and balances are in place. I do not want to have a technology that is enabling exploitation of people of lower income, because the organs can now travel a lot farther across borders.
Oh, right.
And so we need to be extremely mindful of the ethical context and legal context. And I predict that will remain a bigger challenge for longer than the cost of the technology itself. We have to remember we're dealing with life at both ends here. Someone's life is ending, and someone's life is being prolonged. And we've got to make absolutely certain that the ethical context is right first and foremost.
So who do you need to bring onto your team in order to help you with that situation?
Fantastic key opinion leaders from around the world with a great geographic diversity, politicians, the opportunity to start thinking about transplantation not nationally but globally. So established organ transplant organizations like UNOS, like Eurotransplant, can play a massive role in saying, okay, how can we take our learnings from doing this in a population of 300 million in the US and 500 million in Europe, and actually help bring other countries into that same well-established regulated framework, so we can optimally utilize the technology to benefit all territories.
So what you've just said ties in nicely with this next question, because you've mentioned a bunch of other professions. They've not given their name, but they've said development like this takes over 15 years across numerous disciplines. Is the UK research funding structure able to manage this? Well, that was a shake of the head.
That's a bad question.
You may not have been.
No,
Yes, with tweaks. So this is not a diplomatic answer, unlike some of my previous ones, on which you very quickly commented. I think we've been extraordinarily fortunate, and probably more fortunate than any comparable technology anywhere else. So the company was able to achieve sustainability as a company on a minute amount of dilutive funding, because the UK ecosystem is so amazing at providing non-dilutive funding to great technologies, from UKRI in the very early stages. Funding bodies like EPSRC, Innovate UK really help develop these technologies and nurture them into prototypes, to the amazing mechanism that is the previously established National Institute for Health Research, NIHR, that then takes those technologies and helps pay for validating them in early human trials and in later stage human trials. It is actually possible to travel most of the pipeline on UK national funding only. The one bit where we are falling over is what happens between the end of that funding, which is actually having had a technology that is now tried in clinical trials, ready to be rolled out, and being able to get reimbursement through this mechanism called NICE, that has to then approve how hospitals can pay for the very technology they helped prove is actually effective. And very often in the UK system, there is between regulatory approval and NICE approval a 3 to 5 year gap, which is completely counterproductive because it means everyone else gets access to UK-derived science first before the UK patient on the NHS can actually access it. And that's a problem we have to fix politically and effectively.
Alison, Pankaj, what do you think?
So hearing you talk through the UKRI and Innovate UK story, certainly I think I happen to be on the board of one of the catapults. It is Smart Cities and Transport Catapult, but there are medical ones. There's gene therapy and something else. There are 2 catapults focused on advancing
Cell therapy.
cell therapy, yeah. And these catapults will connect the brilliant ideas in university with maybe small startups with industry to actually launch it into the next stage of they call it the TRL, the research levels. That is a mechanism that exists, and let's hope the changing of governments continues to enable that to happen, because it is a very good way for the UK to actually benefit from the brains that we have in the UK to turn it into commercial reality.
Pankaj, I'll let you have the final word.
I know. I mean, I totally agree with what you were both saying. I mean, funding is always an issue, isn't it? And I think trials are time-consuming. They do take a lot of expenses and take many years actually to come to fruition. As your trial in Nature that was published, the randomized trial that you did, yeah. I think again it's important to think about having a good team and answering an important question, but also thinking of trying to do small steps, do them well. And think about other sources of funding, not just the typical bodies, NIH or Wellcome or MRC, but venture out and go and approach companies and see if the people will be interested in supporting you, and build up a good team of postdocs, I think, and researchers from different disciplines, and collaborate. I think that's the biggest thing.
Very good. There's just one final point. It's not a question. I'm just going to make a point from someone who's called P. They've said, as a transplant patient, I'd like to say well done. And thank you for this incredible innovation. It's important to hear of lives not just saved, but lives that have continued to live and live well, which I thought was a nice note to end on.
Incredible. Thank you.
Yes, I wish we could take more questions, but I'm afraid we are running out of time. Thank you so much for sharing your time, your excellent knowledge, your anecdotes about sleeping next to pigs and A4s. Please give it up for our fantastic panel. I also want to say thank you to the Academy for hosting us, and to the Worshipful Company of Engineers and the MacRobert Trust for supporting this event. As we alluded to earlier, nominations for next year's award are now open. Maybe next year's winner is here in the room, who knows, or watching online. It's time to say farewell to the audience who are watching online, but good news, everyone is still here, because there's drinks and there's snacks next door. So thank you so much. I hope you can hang around, but if not, have a safe journey home. Thanks.